Hello, welcome to the channel. Lately I've been collecting a set of stock Cleveland intake manifolds so I can do an evaluation test on the intake manifold and the head combined and give you guys a great deal of information about how the manifold works with the adaptation when it's connected up to the cylinder head, because just doing the porting and work on this without including this is pretty pointless. So hopefully that's some stuff that's up and coming. However, one of the biggest things that I have when doing porting on cylinder heads, I've got quite a massive varied forms of cylinder heads, from the 4AGE 5 valve and the big port 4 valve, and you got the 4V Cleveland, 2V Cleveland, and the big port Holden, and the factory old little port. No, this is known as the old VN 5 litre. This is a 308. And then just for fun and giggles, there's an Essex head. So we've all got all these port sizes on all sorts of various cylinders. And when you do port work on them, it's kind of like looking at the last 2 pages of a mystery. And you may know the end, and you may know all the best part of the book, but you kind of forgotten the journey. So I'm going to have to take you on a bit of a journey, because this one here has never, I have not seen a proper analysis as to why Ford came up with this cylinder head design. So this is what this video is going to be about. So it's going to be a long one, and it's going to be complicated, but it needs to be done. So let's get into it. One of the most fundamental aspects of any engine builder has to understand is the process of the air and fuel ratio. But more importantly, it is this aspect. It is a weight aspect. So there's 14.7 pounds of air to 1 pound of fuel gives us our air fuel ratio. It is not a volume thing. And the reason why is because air conforms to these 3 principles. If we have a set volume, then if we alter the pressure, if we increase the pressure, we can make it heavier. If we decrease the pressure, we make it lighter. The same with temperature. If we decrease the temperature, we make the volume heavier. If we increase the temperature, we make the weight lighter. And for all those people running water injection, humidity. When we add water, we increase the humidity, we decrease the weight of the air. And that's why whenever you do water injection, and only water injection, you lose horsepower, because you lose the engine's ability to consume a set quantity of weighted air. So why the confusion? Well, the greatest one is that we can measure air pressure, and we can measure volumetrically through our flow bench the CFM calculation and how much air we can pass through a cylinder head into the cylinder. However, what winds up in the cylinder is the real mystery, and that is where we will get to now. So for me, I try my best to live by this rule when it comes to engine building. So energy cannot be created nor destroyed. Now, where this becomes apparent is in our induction cycle and also the exhaust cycle. And where that becomes apparent, I will now make clear. This is an old book of mine that I grew up with in my learn how to read days. And in it is a very easy explanation of our 4-stroke, 4-cycle engine. So you've got pull, squeeze, turn, push, or effectively you got suck, squeeze, bang, blow. The point that we're going to look at is this one here, pull. For air to be drawn into this cylinder, this piston has to go down. It creates a void in here of negative pressure, and then air from in the atmosphere is then wanting to fill the void, and so it has been drawn into the cylinder. The point that I want to make on this is that the energy from the piston moving down the bore is being used to pull air into this cylinder. In other words, this is parasitic loss. This is a pumping loss. Okay, so the engine has to consume power to be able to draw in air and fuel for it to burn. I don't like using things of other people's hard work without their consent. So if you do your best, actually go and buy David Vizard's stuff, because he is simply the best when it comes to not just finding out this stuff, but also explaining it in a way that we can understand. So from his building horsepower book, I'm going to flip over and show you this. And it is an extension of what I've just shown you. It is 5 cycles, and this one, he's classed this as the 5th one, but I'm going to class it as the first part of the induction event, so which is the exhaust driven. So this is our scavenging phase, and then we've got the piston driven intake stroke, which then goes from when your exhaust closes all the way to when your intake closes. What I am proposing to you is a new way of thinking, because this is more in line with the first rule that I posted up about energy not being able to be, you can't create it nor destroy it. So the point being here is that we are looking at port speed and how to be able to generate port speed by drawing air into the piston, into the cylinder, and that is being done through our first phase, which is the exhaust scavenge. The second phase, which is then piston driven. The point that I want to try and make is that these two phases are what we'll call is, I would say, a pumping loss, but it's not quite true, because this one doesn't actually cost power. We're taking advantage of the leaving exhaust to generate a negative vacuum to be able to draw in our fresh charge. This part here is where the engine is consuming horsepower to draw in air and generate higher air speeds through our port. However, the piston, when it goes through its cycle of turning, it begins to slow down past 90 degrees of crankshaft, and when it does this, we are then moving into the ram phase, and this is where the energy in the port we're now going to utilize it to continually push air into the slowly increasing volume cylinder to be able to fill it to maximum before we close the intake valve. Now, I've said in previous videos that the fastest point in which a piston is moving is at about between 70 to 75 degrees crank rotation. This is due to the combination of both the rod moving away, which is promoting falling, and also the piston being pulled down because of just the natural arc of a circle. However, when we look at this, we take the measurement from when we have a top dead center, and then the measurement of how far the piston goes down from being at 90 degrees, which is our half stroke. We actually find that in our first 90 degrees of rotation, we actually draw in 58% of our displacement. Now, this is specifically for a 351 Cleveland. I haven't done it to a lot of engines to verify that this number is absolute for everything, but on another engine, I think it was an Essex, I did a very long rod experiment, and it came up to be quite close. It's within, I'm going to say it's within 55 to 60%. So the point that I'm trying to make here is that in the first 90 degrees of rotation, we're actually drawing in more than half of the displacement, which means we're going to be putting a lot more energy into our intake port than what we may have first realized. This head scratcher of an equation is probably something that does need explanation. So this one here, we have our single cylinder displacement of a 351, which is 43.98 cubic inches. And as explained in 90 degrees of duration, it is 58% of this. So that's what that part is there. Now this part here is, we are taking how long a crankshaft takes to move 90 degrees at 6,000 RPM, and we're going to convert it to 60. So what we are actually doing is we are looking at how much air an engine is going to try and consume in this space of time, and then we're going to convert it from cubic inches to cubic feet. So how much air do you think that we are going to, how much air, which is that, is going to need to be drawn in if we were to take this time and we were to stretch it out to 60 seconds? How much do you think in CFM it's going to be? You can run your numbers to clarify, to see if I actually have this correct, but I got this number here, 354 and a quarter, just over 354 and a quarter CFM. So the piston driven demand at only 6,000 RPM is substantial, especially when you compare that a 4V at peak lift is 300. It's still short. So if that being the case, then the piston driven energy is able to pull more than 28 inches, and the reason why I can say that is because our 300 is at 28 inches and this is commanding more, so the engine is going to be able to draw in at a higher rate than 28 inches, and that's something that I'll get to now. You'll have to excuse the trestle, and we've got rabbit cages over here. So, but anyway, this is where things get interesting. So the point of what I'm trying to show here is that both of these, this here is 90% volumetric efficiency, but so is this. This is 98% volumetric efficient as well. So the point that I'm trying to raise here is that an engine doesn't see this. Okay, this is something that we measure on the dyno. We can put our devices on there and we can work out how much airflow is going into the engine, and from here we know how big the engine is, and then we can simply do our math of going, that's the engine. It's in the torque and horsepower video I spoke of total airflow, which is your engine displacement times RPM divided by 3456 for a 4-stroke. So you do that equation and then you work it out against what you've measured, and then you can work out to see if the engine is ingesting more than its fair share in the size of the engine, so it's acting like it's a bigger engine, which is above 100%, and in most cases we work underneath it. However, an engine doesn't work like this. This is just us trying to work things out. This is how an engine works. You've got 14.7 psi from atmosphere, and then by the time we get air down the port and into the cylinder to be able to be compressed, it doesn't wind up being 14.7 psi anymore. Why? Because when it goes through the intake port, it gets stretched, and that's what a vacuum is. It's stretched air. It's thinner. And then by the time we get our air pressure into our trapped cylinder, because when we close our intake valve, the actual pressure in that point for our 351 at 90% volumetric efficiency is 13.23. We've lost over 1.5 psi in the transfer. So the point being is that a 4V Cleveland works on this principle. It is trying to get maximum air pressure from outside the engine into this point here. And this is where the fun begins, when it does, when we put the wrong camshaft in. I'm going to utilize Mr. Vizard's book again, and in this example here he's showing how a piston, which is not moving at all, we have quite a lot of port velocity down low. This is our exhaust scavenging effect down here, and then as our piston speed increases, so does our port velocity. But as said, once we get to 90 degrees, we actually are starting to taper off. And as we continue to go down, remember, once we get to 180, which is the bottom of the cylinder, we still have a fair amount of ramming force, which is 200 feet per, 200 feet per second still going into the port, into the cylinder. 30 degrees after bottom dead center, we're actually starting to run out of air. And in fact, this lump here on this demonstration is actually showing that port air is in reversed. So what this means is that cylinder pressure is now going back out the port, and we are losing trapped mass. So whatever this camshaft is, it almost deserves to be, it needs to be trapped, or bring the camshaft and get it to close earlier, and you'll actually get more trapped mass in there. But the point being, and the point that I want to show you, is that after we get past our exhaust scavenge, and then our piston driven intake, and then it goes into our ram phase, and this is when the energy in the port is being utilized to fill the cavity, which is then slowly beginning to grow. But in doing so, the port is losing energy as it is pressurizing the cylinder. Now, the point being is that when you have, as what it's shown, is that when you have the correct port size for the application, you get a good amount of energy, and then you can have a long ram phase. Now, the 4V intake port, because it is so big, we don't get the peaks that we can see on here. It peaks earlier and doesn't get as fast, which means it has less energy, which means this is going to fall a lot quicker. So what does it actually mean? It means that a big port, the 4V Cleveland specifically, commands a early intake closing point. Down here under my bench, I have done a recent upgrade, and now I have 4 vacuum cleaners. So what does this actually mean? Well, each vacuum is about 2 kilowatts, which is 2.3 horsepower, give or take. It's actually, no, take it back, 2.6. So let's say, for ease of math, 2.5 horsepower per vacuum cleaner. So when I have a cylinder head on the bench and we are drawing in a certain amount of airflow, this is something that I'm going to have to do in the future to show you, is that I only need 2 vacuums to be able to draw in this much air. But as we get the valve and we open it up, that's when we can turn on the second vacuum to draw in more vacuum. However, this is actually a direct comparison between an engine's horsepower, not horsepower potential, but the RPM potential. Because as I said earlier, our engines, you can't create or destroy energy. So if I have 10 horsepower down here to generate the flow requirements of a cylinder head, then an engine is going to have to consume 10 horsepower to get the same requirement. And this is something that you don't get to see on any other bench, is most of these guys don't take this into consideration. But this is quite clear, is that if you can generate a lot of air, you can generate a lot of airspeed with just this amount. But when you start to put more RPM, which is more energy into the port through airspeed by the RPM of the engine, the energy in which the energy that's required goes up because there's a restriction on the amount of air that you can get through the port. Excuse me. Oh. Yeah, so from now on, when I'm going to be doing my porting, I will do a full lift with each 4 that I can actually do. And I will evaluate it so that when an engine consumes 2.5 horsepower, it'll be getting X amount of air, Y, Z, and then T total. So in the future, I'm going to wind up with a lot more information than just a simple flow chart like this. So we'll get on to, and now I'll get on to the final piece, which will be the analysis of all that information and how it's going to be relevant for you. In this book, in the back of it, there is actually a very good table. So this tells us our test pressure and the CFM per cubic inch, and it'll then tell us our velocity. Now, the point that we need to make here is that this is classed as our 100% discharge of coefficient number, okay, and it steps up all the way through that. If we are at here, that's normally rounded up to 146, but as you can see, as we increase our test pressure, so does the CFM number goes up. 35, 40 to 50. So if we had 50 inches of water, we would be able to pass 195 CFM per square inch of port space, and would have a port velocity of 468 feet per second. Now, if you don't know what that is bordering on close to the speed of half of the speed of sound. In fact, if we actually get up to here, 512, and that's at 60. 512, and that's at 60. Point of this being is that it is showing us is that if you want more velocity, you increase the test pressure. This is on the flow bench. On a running engine, if you want to increase the velocity, increase the RPM. That will then increase the demand, the CFM demand through the port, which will then increase your velocity. So this is just a mock-up really of just the basics of how the port size and your camshaft timing, namely the intake closing point, needs to match the port size. So if we have a small port which has a lot of velocity but doesn't have a lot of flow, we need to take advantage of the fact that there's a lot of energy in the flow, and we can get it to ram, and we can get it to keep ramming till late. But if we have a large port, then we need to shut the intake valve off early to generate more torque, because this way, if you take your late application and you put it on a large port, you're going to lose torque due to reversion. And if you take this one here and you apply it to a small port, you will lose torque because it hasn't got time to get the air into the cylinder. And if you're going back to how the pressure is from the outside to the inside, if we cross these 2 points, you are simply denying the ability of atmospheric air pressure to be able to get into the cylinder and be trapped. So the wrap up of this video, I suppose before I do, there needs to be some considerations that I need to get across, because intake closing point isn't the only thing that affects these, especially this one here too. They actually share quite a lot in common, to be quite funnily enough. But the point being is that if we have a large port, that means the pressure inside this port is going to be at a higher pressure than a port that is this shape. So what does this actually mean? Well, this has high airspeed, which means it's got a greater ability to tear apart and atomize the fuel that is going down into the cylinder. This gives us a better homogeneous mix and will burn nicer. This one here won't do that. So that means it's going to deliver bigger blobs into the cylinder that are going to burn slower. So this port is going to favor a carburetor that can atomize really, really well. This one will benefit from it, where this one here isn't really going to care that much. Moving on to camshaft timing. Now if we take this one here, which is our 16 valve 4AGE big port, now the race versions of these, when you say race versions, but the higher RPM, the high performance aftermarket models, so they were the ones that the guys that were doing the race work on this, they had an intake center line of close to 100. Okay, these guys here, now if you try and find a camshaft that's got this and it's on 100, that's had you out of your mind. And especially this one here, you'd be nuts. That is way too early. But that's the difference, is that this one here may operate at 112, intake center line of 112, may do all sorts of awesome things, and have a really big camshaft like 280, 290 degrees, and get away with 112. But if you were to do the same with this, run this at 112 with a 290 degree camshaft, the thing would be an absolute dog. Why? Because the airspeed is low and it would just push all of the air that would get into the cylinder. It's just not closing the intake valve, and it will just push it all back out into the intake. Simple as that. Less trap mass, less torque, less horsepower. Simple as that. Moving on to this one. This is the 5 valve version, which means it has heaps of curtain area for air to get out the cylinder. How did they combat this? Well, this one here runs what other people, or in fact what most automotive manufacturers are doing today, variable cam timing. This was a very simple affair, of course. It just simply twisted the cam and it closed everything earlier, opened everything earlier on the intake and closed it all earlier. What does that do? Well, stops reversion. Greater trap mass gives you an increase of torque. It's that simple. Honda does the same thing. No one complains about them for the fact that they've got gigantic ports, but they have the system which is called VTEC. So they have a very small camshaft. Very small camshaft, very low lift, and it generates enough torque to get you into the zone where you then start to utilize the airflow of this. So the point, the biggest point I'm trying to make, is that start with the best cylinder you have and then build the cam for it. Don't go the other way. Don't have a cam and then try and build a head for the cam, because it will always end in disaster. Start with the best cylinder head first and work from there. The other one too is you have to take into this consideration as well. These two here, they're over 50 years old. In fact, I think these are close to like 55 years this year. This is a 55-year design. That was designed in the 80s, which I think was actually a takeoff of the BDA, which dates back to the 70s. So again, it's 50 years old. This one here was designed and built in the late 60s. Again, well over 50 years old. This one here, this was a design in the 80s. And surprisingly enough, looks really similar to an LS. It's quite freaky, isn't it? And then we've got this one here, which is, oh my goodness, this dates back to, this is another design, this dates back to the early 60s. You got to remember though that this head was designed, it was potentially looking at being diesel design, so they weren't really looking at airflow. But that's another, that is another bag of nuts and bolts to deal with later. So yes, so that is the point of the video that I wanted to make, and it's really just an extension of when I did the port stuffer and did the flow rates and everything like that. But for this reason, this is why Ford, when they made this cylinder head, they made it the port size that they did, because they have a great understanding of the geometry and how the piston moves, how much how much CFM demand a piston can command at high RPM, and so they designed the cylinder port. There is also one, I'll call it cheeky, but whether Ford knew or not, I don't think so. I think they were just covering their basis. But when you go back to the 1960s, Chrysler had their 426 Hemi, Chevy had their 427, and Ford were also in designing and built their 429. They were running I think they were doing the 427s as well. But anyway, 7 litres. What was the point of 7 litres? Well, 7 litres was the displacement limit set by NASCAR. Ford was looking at they were basically looking at it going, how do we get big block airflow out of our, dare I say small block, but how do we take a smaller displacement engine and get it to consume big block air? Well, that's what they came up with. And the reason for this, isn't whether they were covering it, is as time moved on and after this had been developed, NASCAR put restrictor plates on 7 litres, which means these things had an airflow advantage over the Chevy head that was on the 350. And I'm trying to think of what Chrysler ran. I can't remember if it was a 340 or they just ditched development altogether. I really can't say, but I think Ford just hedged their bet, and these wound up being the go-to NASCAR engines that was a displacement of 358, and the reason for that is that they were unrestricted, and that came about from the fuel. They were trying to cut back fuel use because of the energy shock of the early 70s. So yeah, there's a bit of engine knowledge hopefully to chew over. Hopefully it's enough really to get on with, and hopefully this one here will be the next project that I'll get onto shortly. Hopefully I haven't bored you to death, and I hopefully hopefully I got my point across in a way that you can understand, and now you have a little bit more knowledge than your race competitors, and you can apply it, and then you can win in your division of racing, whether it be drag racing, rally, whatever. But anyway, until next time, keep working, and I'll see you in the next one. Bye.